right? So we discussed about the fact that we can represent the Yule Walker equations using this matrix. And this matrix has like n equations, and the n equations will be used to solve the values of unknown parameters of the system. And if you are trying to estimate the values of A1, A2, A3, A4, likewise up to AN values, then we can use n equations to find those values. Also, this equation that we earlier derived as B can be simplified into this form where we make the L equals 0, and we can write that relationship like this. So this equation also can be used as a support to find these unknown variables. So using those unknown variables, we can either find, like we can write this equation where the capital R matrix dot simple A vector, which is the combination of all the coefficients A1, A2, A3 up to AN, is equal to the minus simple R, which is the matrix or vector given in here, which is like combination of the autocorrelation values. So we have a question where we want to find the values of coefficients of A, simple A, we can find that by taking the inverse of capital R and then taking dot product with the simple R. And also, so if we find like that, we can get a fixed solution to the unknown parameter A, and that fixed solution can be, that closed form solution is obtained using that analytical method. If we use analytical method, we can solve all these equations using mathematics. We can find a closed form solution, and we can find a fixed output to the unknown parameter. So if we are using mathematics, we can get a closed form solution that will govern the input parameters and relate them to the output parameter A. So there will be some equation that will help us to derive the parameter values of A. So that form is the calculation of solutions using the analytical method. If we have the MATLAB commands or MATLAB environment, that also can be used to find the analytical, that also can be used to find these values of A. So that one, of course, we'll use the numerical methods to find the values of A, because MATLAB will use some, iterative calculations of the parameters in its tools, and it will iteratively calculate the values of A and give a value of A, which is the most optimal value. So this ARU command can be used to find the coefficient of A using MATLAB, and there are other commands also that are used, and we will discuss. So we will try to calculate the values of parameters, unknown parameters, using the analytical method first. So we will discuss that example. Any questions up to that point? If you have any questions, let me know. So I'm going to discuss this sum. I will put this in the chat. Okay, so there's the AR process that we are considering, and that AR process has this desired response uh, signal, and that is given by this equation. And the V is denoting, V1 is denoting white noise process with zero mean and variance of 0.27. The signal is fed into a channel with output Xn and V2n, right? So the signal is input to a channel, right? With this output Xn plus V2n. So the Xn is further given by this equation 0.9849458 Xn minus 1 plus Dn. And then V2 is another white noise process that is modeled by the zero mean and 0.1 variance. And then we have to show that Xn is like AR process that is modeled by this equation. And then we have to find these matrices, correlation matrices and cross correlation matrices. And then we have to find the optimal filter that can give the same, statistics of the input signal at the output. So we will first, I will try to first draw a diagram that will show this scenario. And then I will try to explain how we can solve this problem. In the meantime, you also can try to solve it on your own. So please mark your attendance in the Google form in the chat. So the first step will be like writing down all the equations that are related to the, system, right? So I'm gonna write down most of all the equations that are related. So these are the four equations that are there. First of all, we are asked to find what xn is. So in order to find what xn is, so in here, the question is asking us to find xn in terms of its past time samples of x itself and v1. So currently we have this equation that has, this expression, but in here we have dn, which is something that we want to remove and substitute with samples of x and v. So for that, we are going to take the condition that is in the second equation, and we are going to substitute dn with, or we are going to take dn as a subject, and we are going to substitute xn related terms in this equation, second equation. So what we're going to do is we are going to take the third one. We are going to find dn in terms of x, and we are going to substitute for all the terms of where dn occurs in terms of x. If I take this as c, so in here, the dn minus 1 is considered. So once you substitute dn minus 1 in here, we have to take the relationship between xn minus 1 in here and xn minus 1 minus 2 in here. So So by solving this equation, we can get the equation that is mentioned in here in a similar manner. So we will get something like 0.799 here, but it will be almost equal to 0.8. So we will get an equation like this. So D is in the form of sorry. So sorry, I think okay, so now we are going to consider a system like this. So we have to like find the correlation matrix at the input of this filter, and that filter coefficients we need to find later, the optimal filter coefficients we have to find. So the input to the filter will be un, and that un will be combination of xn and v2n. So xn is signal, which is like uh, a random process signal, and this v2 is a white noise process, white noise random process. So we know the V2 variance, and therefore correlation matrix of V2 can be found. Xn, of course, we don't know. And therefore we need to find using the Xn, using the Yule-Walker equations. So finding the autocorrelation matrix of Xn is the second step. So in order for us to do that, we can write the Yule-Walker equations, and we can solve those equations. So that in the equations we derived earlier. So we can write this equation first, which is the first equation that we considered, that gives us the relationship between the x's and the sigma value of the white noise. So this equation we can first consider. So we know for a fact that this form that we have obtained about the xn, right? It is about the AR process, right? So AR process, this is AR process. And for this AR process, we can write this equation. We can write this equation where the A values, AK values with the RXX values give the variance of V1. For this equation, we can write this relationship. For this equation, we can write this equation, and we can, consider this as 1. So, we can also mention that where A1 is minus 0.1 and A2 is minus 0.8. So therefore we know the values of A values. So we can substitute that and form an equation. Also, we know the variance of V1, which is given to us, which is I think it's 0.1. V1, yeah, V1 is 0.27. So using this equation, we can write Rxx0. Rxx0, the component A naught is 1, so we don't have to add that. So in here it's 0.1 minus 0.1, Rxx1 minus 0.8, Rxx2 equals 0.27. This is one equation. Let's say it's P. Let's say it's P equation, right? So because I have used ABC in the above equations, I'm not gonna confuse those equations with these equations. And then we can write the Yule-Walker equations. Using the matrices, we can form a matrix considering the Yule-Walker matrix. So we can form two equations from this. So if we consider this first line, we can solve these equations, and we can find the values of Rxx0, Rxx1, and Rxx2. There are three equations, and we can find those values, right? So we have this equation, this Q equation, and the R equations. Using P, Q, R equations, you can find the values of Rxx0, 1, and 2. So once you calculate them, you get some answers. So you check whether you get these answers. I'm getting 1, 0.5, and 0.85. So I will write that. So the correlation matrix of X we can write. The correlation matrix of V2 is RV, let's say RV2, which is equal to the RXX or RV, sorry. So, the correlation of white noise will only appear at places where the autocorrelation is 0, or else we can call RVV 0, which is actually the sigma squared of the RV, and therefore we only have the values for that element. So therefore actually we will have the value of sigma squared V1 and sigma squared V1 and sigma squared V1 in all the diagonals, and so we can form a matrix like this, which is similar to this input signals matrix, because we need to add these two signals in the same order, so that we can get an output UN output signal from these two signals. So this is what will be that. So we'll be having 0.1 in the diagonal, and all the other elements will be 0. So the input correlation matrix to the filter is going to be a combination of Rx and RV2. So the step 3, right? Step 3 is going to be find the correlation of V1, let's say. So step 3, correlation of v1, v2, and so the input matrix Ru will be a combination of Rx and Rv2. So it's going to be the addition of these two matrices. You can calculate that and you can put it in here. Next one is compute the 3x1 tap weight vector of the Wiener filter. No, second one is finding in the first question, we have to find the cross correlation vector also between the desired response and the tap inputs. So we have to find the cross correlation matrix or vector of the UN and DN. So it's a vector. So we have to find this vector. For this, we have to consider that the expectation between the, cross correlation means expectation between UN and DN. So since we are going to consider past values of UN, we are going to consider the cross correlation of UN minus K with the DN, because we are going to consider past values of UN, or not only the current value, but also the past values included. So this expression includes both the current value of the time and also the past values of the time. So the components of UN, which are in the past also are considered in here in the cross correlation vector. So each vector component we will call as P minus K. So if you are considering past values up to 3, we can calculate P0, P minus 1, and P minus 2. 3 past values, including the current one, we can find using this, by substituting K equals 0, K equals 1, and K equals 2. So we have to now find the values of this expectation. So the thing is, like, we can substitute for UN the xn values. Using x, we got a relationship earlier, so that we can substitute in here. Basically, we can substitute xn plus v2n in here. So for the case where k equals 0, this is basically un. Un is equal to this xn plus v2n. We can take multiplication here, and then this one will equal to the multiplication of xn dn plus v2 dn. So expectation of xn dn remains, and other thing becomes 0. Xn dn plus 0, mainly because there's no relationship between v2 and dn, because v2 and dn are independent with each other. These are independent processes. So similarly, we can write the equations for this, where you write xn minus 1. So in here, actually, we have to first solve this. Then we can, I think, go to the next, components x and d, and we have to compute in here. So for that, we can again, substitute instead of xn, we can substitute values for the dn using xn only. Xn we can multiply with dn, but dn we can represent using xn only. That I think we did earlier. So which is like dn is xn minus 0.9458 xn minus 1. Right? So in here we can see, we can get the product of xn to xn, which is rxx0. And then we can get the product between xn and xn minus 1, which is minus 0.9458. So 0.9458 constant remains. And the product between xn and xn minus 1 gives us that it is the autocorrelation with the time lag of 1. So this is the P naught value. So since we know the rxx0, rxx1 values, we can substitute those values in here, find this P naught value. Similarly, we can find for P minus 1 and P minus 2 by substituting for this equation, and we can get relationships for P minus 1, P minus 2 in terms of rxx values that we computed. So rxx1 minus 0.9458, you can calculate on your own and you can get these relationships, right? So like same thing that we did here. So if I'm going to write the E x n minus 1, take the expectation with the x xn minus 0.9458, which is equal to rxx1 minus 0.9458 rxx0 . So you can find the values by substituting the values that you know of rxx1, 2, and 0. And by doing so, we can find the final vector of P, and that one will be equal to P naught, P minus 1, and P minus 2. So this vector P that we get here is a cross correlation vector, which is showing the cross correlation between UN and DN. So this value we can find. So we know the values of our input, R matrix, and the cross correlation matrix. So we are asked in the part 2 to find the optimal filter coefficients. So to find the optimal filter coefficients, I think the next step will be using the Wiener-Hopf equations. So Wiener-Hopf equations can be used once you know the autocorrelation of the input to the filter and the cross correlation between the output of the filter and the cross correlation between the desired signal and the input of the filter. So that one, those are given by this, P is the cross correlation between the input of the filter and the desired signal. So that P vector is that. So we can write the optimal filter coefficients using those matrices that we know. So R inverse P will give the optimal filter coefficients. Right? R inverse P will give the optimal filter coefficients. So by finding that, you can find the value of W naught optimal filter coefficients. So this one you can find using and then we are asked to find the minimum, mean error. So minimum mean error, that equation also we discussed in the Wiener-Hoff equation. So that is given using this minimum mean error is given as the J mean, let's say. So it is given as the desired signals variance minus the transpose of the cross correlation matrix with the optimum filter coefficients. This also can be written like, so now we know the variance of the desired signal. Variance of the desired signal we have to find out. So the variance of the desired signal is given by this dn into dn equation, right? So expectation of dn into dn gives us the variance of the dn signal or the variance of the desired signal. And then pt is the one that we know. So we can take the multiplication between p vector and this one. So we can find this, value that comes here. So the value that we have to find is this desired signals variance. So that one we have to find using the known things. We have to substitute dn with the xn values. So we know that xn is denoted using this xn minus 0.9458, xn minus 1. So this one you can take again, and you can take the product of this, and then expectation of different individual components will give us what we require here. So this will relate to different, values of xn squared and then xn into xn minus 1. So in here, this comes 9458. So it should be into 2 as well, into 2 into, and then xn minus 1 squared into 0.9458 squared. So this one we can find in here. This is rxx0 minus this one will be 2 into 0.9458 rxx1 plus this one 0.9458. This one is rxx again 0, because we are taking the multiplication with the same time sample. By solving this, you can find the value of this sigma square d. And once you find that to be in the range of 0.9458, 9487, so it will be 0.9487, then minus this pt is like a transpose of the column vector, which means that this vector will be in this direction as a row vector, and the coefficients will be, we know those coefficients already, and we multiply with a column vector. So in here it's 0.377. We multiply with the optimal filter coefficient that we got here, which is 0.738 minus 0.803 and 0.138. So in here also you will get a constant at the end, right? So after you do the subtractions, you will get some constant value as the error value. So the minimum error value, J mean, is equal to 0.15. Right? Any questions up to that point? If you have any questions, please let me know right now. Right?
Hello.
So yes,
How did you calculate the P minus 2 one?
in here, right?
Yes.
So
These values. I guess I'm asking these values. How did you get?
yeah, so you can substitute, like I got this equation, right, for P minus 2. So
Yeah.
Rxx2, Rxx1, I know already from previous calculations.
Oh, okay. Okay.
Right, so this like values calculations of, I mean the P vector, W naught vector, all those things have been done using this, calculations of equations like mathematical, uh, algebra and simultaneous equation calculations. So we have used analytical methods to find the values of W naught, for example, optimal values of W, and so on. So this closed form equation has been taken using analytical methods. So this sum has been solved using analytical methods. So most of the time, once we are doing using our hand and manually, we are using these analytical methods. So the same kind of things can be used. Uh, we can use MATLAB commands also to find these same parameters. These same parameters can be approximated using MATLAB simulations also. So there's like some simulations that you can see in MATLAB also that you can use to estimate these parameter values. So there are two methods, numerical simulation methods and analytical methods. So in the numerical simulation methods, most of the time, you will be like approximating the values of the solution rather than finding a closed form equation that will relate the input parameters with the expected output. So in numerical methods, sometimes you will have some approximations. You will assume some things and you will approximate the output. So exactly the output might not be coming, but a very close value to the output will come. So I mean, analytical solution gives us the exact solution. So so that is what also need to be understood. So if you have any questions about this calculation, let me know right now. I'm going to MATLAB simulations next. So this is a page in the MATLAB, MathWorks website. So this is about linear prediction and autoregressive modeling. So we were talking about this autoregressive modeling, AR processes, basically at the last end. So in here also this AR modeling and its concepts are presented. So how we can use MATLAB to process an AR process and get the optimal filter coefficients that can give the desired output from the filter, such that the output from the filter is almost equal to the desired signal. So this says that you can find the AR model using Yule Walker method. So we can use the command AR Yule to find the coefficients of the process and estimate the unknown parameters. So we can use these kind of commands and we can and then in here there's this uh, situation where we are finding the optimal filter coefficients, right? Optimal filter coefficients that gives us the desired signal at the filter output. So these codes can be used to find the optimal filter coefficient. So in analytical method, recently we made the sum and we found the optimal filter coefficients. So same kind of a process can be done using these commands in the MATLAB. And this figure in here shows that the actual filter output, which is given from the blue lines, the actual filter output of the signal is given from the blue signals. And it can be, like, estimated using the, like the uh, the designed designed model that we designed with the optimal filter. So what I mean by that is that whatever the frequency components that are there in the input signal to the filter can be estimated using this Yule Walker method, and we can estimate precisely the frequency content of the input signal. So the frequency content that we estimate is given by this red signal, and the already existing one is given by this blue signal. So what we estimate is very near to and very close to the original signal values. So that's about it about the MATLAB simulations. If you require, you can read more on this by going to this, link. So if you prefer, you can go to this link. I will put this in the chat as well. So, or else you can search this title in the Google and you will get it. Linear prediction and autoregressive modeling in MATLAB. So you will get it if you search for it in the Google. So with that, actually, I would like to end today's session. So if you have any questions, you can let me know. And with regard to the model paper, I will give that during the next week in the LMS. And all the, reference materials you that I I would like you to refer will be given in the LMS. So those reference materials, some of them are also available in the LMS. And so I have given a reference material for this section on time series in this, under this, week number 14 as well. And if there are other reference materials, I will add them under that specific week, and then you can refer that also. And the sample model paper I will get next week, and you can refer that, and you can get an idea, right? So do you have any questions? Okay, so if you have any questions, you can send me an email and I will try to answer your question. Right. So with that, I would like